everyone, and welcome to the first session of the Joy of Abstraction book club. I'm really excited and quite daunted about what it is that I've taken on, but we've got already quite a lot of questions. Some of them are questions whose answers could fill a whole book or indeed thesis. So I'll try to summarize, and I just thought I would, I've got a little, my bookmark is a cut-off mask string, but I've color coordinated myself with my book today. I've got my little beach backdrop, so I can pretend that we're all reading The Joy of Abstraction on a beach. Anyway, I'm very excited and happy and very, very thrilled that so many people have sent questions in. So thank you very much. And without more ado, let's get started. I do think that some of the questions are answered by later parts of the book. And so I hope that you'll bear with it if my answer is a bit brief, and that gradually you'll get the point as we go along. So the first question is about the relationship with how to bake pie. And I think that I said rather briefly on page 10, how to bake pie is not exactly a prerequisite, but having read it will almost certainly help. So How to Bake Pie is my first popular math book that I wrote, and it has a very different target audience from this one, because the target audience for that book includes a much broader range. And so I hope that, and I've heard that it does still have insight for people who are looking for more depth, but it doesn't get very deep. It doesn't get very technical. It gives very, very broad brushstrokes of the idea of what category theory is. And because this book, Joy of Abstraction, is about category theory, the ideas and the technicality, it would help to have read an entire book of my thoughts already on what category theory is for. So the first part of How to Bake Pie is about what math is for at all, given that most people, especially in the target audience, probably had a very skewed impression of what math is from the normal mainstream math education. Then the second part of the book is about what category theory is for. It doesn't really do very much category theory. There is the definition of a category, and there's a little bit about universal properties, but it's very, very, it doesn't get deep, it doesn't get technical, because it's for a very broad audience, and it's for an audience who possibly has math phobia, math trauma, who has no intention of ever getting into anything like a proof. They don't want to do proofs. Maybe they just want to see what's going on. So the Joy of Abstraction is going to get all the way into the technicalities and the proofs, and it's aimed at people who do want to do those technicalities. And so the really broad brushstroke ideas are there in How to Bake Pie, and I do cover some of that in the first part of this book, but I also don't assume that anyone has read it, because, you know, this isn't some kind of very structured college course. I can't demand prerequisites from people. I'm not going to demand that. I'm not going to say you're not allowed to read this book unless you've read my other book, because that would be silly. So that's more or less the relationship between those books. So the next question: can one specialize with an undergraduate degree in category theory? Or is it just a graduate or postgraduate level field? Well, it's an interesting question, because I don't really know how much specialization you can do in any undergraduate degree into one field of mathematics. I mean, I think you can definitely specialize into pure, and you can specialize into a few parts of pure, but category theory would usually only be one class, if you get one at all at an undergraduate degree, which it's starting to happen, and there are some places where there are undergraduate degrees in category theory, but it's unlikely to be more than one course. And so I don't think that would really count as a specialization. You might be able to do one course in category theory and then one sort of directed reading project or some kind of essay, but I don't know that that would count as a specialization. Even at a master's level, it depends what kind of master's you're doing. If you're doing a thesis master's, then your thesis could be in category theory. If you're doing a taught master's, you probably have to do a wider range of things. Next question is to do with abstraction, and at what point does it become category theory? So I think this question, sometimes I will paraphrase the questions rather than reading them out. And I think this question is about, because I talk about how sometimes we're doing category theory without realizing it. And the question is, I think, at what point do we get to call that category theory? And I think the question is, do we need a hard boundary of what counts as category theory? It's like the fact, more broadly, I mean, a lot of questions that one asks about category theory with respect to math can also be asked about math with respect to life. And so you might say, well, at what point do we say we're doing math and not say we're just doing life? Seeing as math is everywhere, is it meaningful to say that we're doing math? And it depends what you want to achieve by saying things, right? So there's an incident on Twitter, of all places, where someone very grumpy said, well, if you even call that math, then everyone's doing math. And I thought, yeah, that's kind of the point. Everyone is doing math. And apparently to some people, that's a bad thing. So some people, of course, want to make math into a very exclusive thing that only a very small number of people can do. And so to them, it serves their purpose to draw a hard boundary and say, no, 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 these things don't count as math. These things don't count as math. No, no, these things don't count as math. Only once you've done fully axiomatized, I don't know, once you're writing a formal proof, does it count as math? As I hope you might know about me already, that's not how I operate. I'm not trying to keep people out. I want to bring people in. And so there are many things that I think count as categorical thinking, whether they count as formal category theory. So I suppose I might make distinctions like categorical thinking as opposed to formal category theory. Formal category theory involves definitions and theorems and proofs, but categorical thinking, well, that's all over the place. And we do that. I do that all the time. So I think that would be my answer to that. Thank you for that question. Next question, there is a question about contexts and about what I mean by category theory operating in different contexts and whether there's a typical set of contexts. I think what I mean is something a bit different there. I think what I mean is that category theory is setting up a whole framework for dealing with different contexts. The whole idea of category theory is that everything we do is only within a context. Everything is contextual. Everything is relative to a context, whether it is talking about politics, talking about social justice, talking about human interactions, talking about the weather, talking about food, talking about numbers. We're always talking within a particular context. And category theory says that it helps us to be aware and draw attention to what context we're in so that we don't accidentally mix up different contexts. That's what it's saying, because math can accidentally or sometimes deliberately give the impression that, and I think we're going to come back to this in the next chapter, is about absolute truth that's true everywhere. And I think that's misleading. And I think there is a sense in which that could be regarded as true, which I say later in the book, but that really everything is within a context. And category theory is saying that we should make that clear. And that's what categories are. So a category is a context. And so the set of contexts that we're looking at is categories. That's what they are. And so anything that can be made into a category is a potential context for studying things. And there isn't really any limit to that. I think it could be anything. Nearly anything. Right. What can category theory teach us about mathematics itself? That's a thesis. That's absolutely a thesis. It's probably a philosophy thesis. Maybe it's answered by my whole book. Maybe it's answered by all of my books together. But I'll try and give some answer about what category theory can teach us about mathematics itself. It's an interesting question. I don't know. Like I said just now, most questions about category theory relative to math can also be posed about math relative to life. And supposing we said, what does math teach us about life? And I suppose if I think about that question, I'm not sure that math teaches us things. I think that math helps us to see things more clearly. And I think that maybe I'm taking the question trying to take it a bit too literally, but I think category theory helps us to find insight. It helps us to see relationships between things more clearly. It helps us to spot patterns. It helps us to see similarities between different parts of math so that we don't have to repeat the work that we've done in one field and then do it all over again in another one, because the category theory goes up a level, joins those fields together and does it at the same time. I think that maybe there are some lessons to be learned from the process of doing category theory. So maybe this counts as things category theory teaches us about math. It teaches us that the relationships between things are often more important than the things. It teaches us that structure is important and that maps that preserve structure are particularly important, and that there's a lot of insight to be gained from seeing which maps preserve structure. I think that it teaches us about good ways of defining things, because it comes up with a way of saying what's a good way of defining things, and that can become a guiding principle. And that answer probably won't make sense until we finish the rest of the book. But I think that, for me anyway, and for those of us who do it from a pure point of view, it becomes a guiding principle for how to do math well. I think that's what it teaches us about math. So now some specific questions working our way through these pages. What would be my recommendation for a curriculum for school maths? This question seems to be from a British person, I think, because it says maths and it says primary and secondary level education. So yes, I have at some point tried to sit down and draft a curriculum that's not based on hurdles, because I think that most parts of maths don't depend precisely on what went before it. They depend on ways of thinking a little bit and the kind of discipline of organized thought processes. But you don't have to be able to do your times tables to really practically do anything else. And so it's particularly egregious that times tables are used as a filter so often, because I think that you can do thinking about numbers and thinking about relationships between numbers, and you can think about shapes, and that's nothing really to do with numbers. You can think about measuring doesn't really involve arithmetic. There could be a little bit, especially if you start doing area, but I don't think there's any real need for it to depend on mental arithmetic. I mean, why not start teaching people how to use calculators? Radical thought, I know. And then there could be things like logic. Talking about how logic interacts is nothing to do with numbers. The idea of turning life problems into math problems, which is called word problems, but the word problems are often so contrived that it's really annoying. But looking at a situation and finding the math in it, in the world around us, I don't think has to depend particularly on anything else. And then there are things like graphs, that doesn't really depend on anything else. I think that different ways of drawing graphs, different ways of representing data representation, and collecting data and dealing with data. I haven't really got very far into high school, but I think one of the big problems with the way that maths is going, and the way it is especially in the US, is that it's so modular. And so if you have to do an entire class on trigonometry before you can go on to an entire class on algebra, or whatever is called algebra, I think that's quite strange. Whereas doing things from the world around us that are interesting, and doing things like looking at the news and seeing what math is in the news, or understanding the maths that is going on if there's stuff that's happening with prices. So you could talk about the cost of living crisis, and you could do things to do with money that is much more practical, but would capture some people's attention in different ways. I don't know, I'm just making things up as I go along, but I think that there are really not that many things that depend on any other things. And manipulating symbols is sort of a crucial part of a lot of mathematics, but making it into an entire course called algebra when it's just manipulating symbols seems to be dull. I think, whereas if you just keep practicing manipulating symbols in different scenarios, then maybe that would be better. I'm not an expert in K-12 primary and secondary education, but I'm pretty sure that it could be done in a way that is much less hurdle-like, taking into account that things can happen at different times in different directions. And I do have a strong suspicion that we should just entirely ditch the idea of doing calculus in high school, because the calculus that's done in high school isn't proper calculus anyway. I understand that the reasons that there's an obsession with doing calculus in high school, especially in the US, which may be partly to do with the big textbook industry. We don't have big pharma, but we have big calculus textbook, and they're making so much money from calculus textbooks that they want to carry on doing so. And I think also that people who are involved, who hold a lot of money in influencing those kinds of things, may well be people who did really well in calculus in high school. Maybe they got a huge quantity of their self-esteem from being able to do calculus in high school. And so they don't want to admit that it's worthless, because then where will their self-esteem go? Anyway, I'm digressing quite wildly. So I think that sort of deals with that question. What would be the difference between abstraction and generalization? Good question. And I did somewhat address that in How to Bake Pie, and they're very related, because often you perform a generalization by means of an abstraction, and often you do abstraction by generalization. But I would say, and I don't use these, I'm not using these words in at all a technical sense. So the only words I use technically are the actual math terms. Everything else I'm using to try and build up a feeling about things. So for me, abstraction is about forgetting details about a situation, and it moves you up a level of, well, abstraction. It takes you a little bit further away from the concrete world. So you forget some details about something so that things become a bit more ideal. And in that way, a lot of things become the same. So you can abstract from, say, an orange and an apple and a tennis ball, and you could say that they're more or less all spheres. I wouldn't exactly call that a generalization, whereas you could abstract from an apple and an orange and call them both a fruit. And I might call that both an abstraction and a generalization, although I'm not quite clear about that. So I think a generalization for me is the opposite of something of a specialization. So an apple and an orange are both special cases of fruit, and that's why I think fruit is a generalization of an apple and an orange. So a generalization is where you broaden your criteria so that more things become examples, whereas an abstraction is where you forget some details so that many things become unified. And there's a big overlap between those things. And I think that in technical category theory, an abstraction is where you well, let me do it the other way around. A generalization is more likely to be where you drop a condition. So you have a situation that's defined by a certain number of rules, and then you drop a rule. And that lets more things into the situation. Whereas an abstraction is where you make something one level more ideal, or you, let's see if I can think of a good example of something that's an abstraction without being a generalization. I mean, I think that something we'll get back to later, which is that co-products are an abstraction of addition. So they're the category theory version of what addition means. Now, they would count as a generalization if there is a sense in which addition is an example of a co-product, which is also true. Now, it's possible that that was much too complicated an explanation, and that would be something better to come back to later. Okay, here's my attempt at a better example that's still specific, but not quite as profound or advanced as the category theory one. So if you draw a graph of a parabola, then you could just sort of draw it as a set of points, and then an abstraction of it might be that you declare that it's y equals x squared. I'm not quite sure about that. But then you might look at x squared and x cubed and x to the fourth, and then a generalization of all of those would be x to the n. And so x to the n, I wouldn't really say that it's at a higher level of abstraction than x to the 2, 3, or 4. It's just more general. So I think that that's somewhat questionable as I think my answer is a bit suspect there, perhaps, but that's what I can think of at the moment. Right, next question. Right. This next question is sort of what my previous slightly too complicated answer was getting at. So someone is asking about 5 plus 1 and 1 plus 5, because on page 18, I say, when we say 5 plus 1 equals 1 plus 5, we really mean that the outcomes are the same. So the question starts like this: does category theory distinguish 5 plus 1 equals 1 plus 5 from 5 plus 1 equals 6? And the answer is it can do. Yes. And so numbers are kind of decategorifications of sets. And if you go to the level of sets instead of numbers, then you look at a set of 5 things and you look at a set of 1 things. And then what we're going to see is that that addition takes the form of a universal property called the coproduct. And that coproduct is canonically isomorphic. So that means the same in a very strong way to the coproduct the other way around. So if you do if you take 5 objects and 1 object, the coproduct of those 2 sets is the disjoint union of them. If you don't know what that means, don't worry about it for now, or well, worry if you want to, but I'm answering this question with a bit more detail than might be understandable if you're really just reading chapter 1 right now. So if you take 5 objects and 1 object and put them together, and then you compare it with what you would have got if you had put 1 object and 5 objects together, there's a very strong sense in which those are very, very alike, because the 5 map to the 5 and the 1 map to the 1 just mixed over. Whereas if you compare that to just a random set of 6 objects, there's no canonical way to map them to each other. And canonical means one where you don't really have to make choices. So if you just have 6 things and then over here you have 5 things and 1 thing, there's no way. You have to make some choices if you want to decide which ones map to which ones. And so in that sense, the relationship between 5 plus 1 and 1 plus 5 is much stronger than the relationship between 5 plus 1 and 6. And this is something that category theory deals with very well. And we'll come back to it when we do the chapter on universal properties, which is a very long way away. But that's one of the first universal properties we'll do, products and co-products. And so the question then says, does category theory not treat similarity as a single dimension? And that's true, it doesn't, but there definitely are. So when we talk about sameness, that will be by isomorphism, and we will see that there are isomorphisms that are canonical in certain ways and others that aren't. And the canonical ones are kind of better because they don't involve us making arbitrary choices. So category theory tries to make things, it seeks things where we don't have to make arbitrary choices. And I like to think that it's because we really don't want to get decision fatigue. I get decision fatigue really badly. I just want to have everything be canonical as much as possible. And that's kind of what category theory does. And the question says, it reminds me of Orwell's, all animals are equal, but some are more equal than others. Yes, I like that, because that's kind of, I like that a lot. That's sort of what canonical isomorphism is saying, that some things are isomorphic, but some are more isomorphic than others, because a canonical isomorphism, if it's good, very good. I think you got it. And finally, in this section of my questions, someone asked, is it taken as assumption that objects have no intrinsic characteristics in category theory? So I want to phrase this rather carefully, because it's not that objects have no intrinsic characteristics, it's that we don't observe their intrinsic characteristics. So they may well have intrinsic characteristics, it's just that we don't take them into account. So when we think about objects in a category, we ignore their intrinsic characteristics. So they could be numbers or they could be animals. Those just do have intrinsic characteristics. We're just not going to take that into account. So that's the kind of specific questions about the text. Then there were quite a few questions about general questions about relationships between category theory and other fields. And I take it that this is because some of you are reading the book coming from other fields, some of you have an interest in applications in other fields, and that's wonderful. I just want to put this caveat in that as soon as you start asking about some other field or some technical term related to some other field, it has the potential to be intimidating to others who don't know about that. So if people are asking questions about, oh, does this category theory relate to this very, very complicated sounding other thing, I hope you won't worry about it, because I'm not expecting anyone to know what these things are. And for some of them, I don't know what they are. Applications of category theory to other fields is not my speciality. My speciality is pure category theory. And so there may be other people and other places that will be able to answer these questions better for you. The internet is there for you as well. And so some of these questions are ones that I will just hint at the answers of what I would answer. So relationships between category theory and theoretical physics. Yeah, there's tons of that. So there's tons of the most long-standing applications and relationships of category theory to other things that I know of are with category theory and theoretical computer science, and also theoretical physics. Now, I don't really understand very much theoretical computer science or theoretical physics, but I understand that there's stuff there to do with topological quantum field theory and to do with cobordisms and to do with trying to understand the shape of space and how it fits together and interactions between particles. If you look up category theory and physics, you'll see tons of stuff. And John Byers blogged about that since before the beginning of the existence of blogs, because he basically invented the concept of a blog, and did this week's finds in theoretical physics, which then involved a lot of category theory. Someone asked about undergraduate algebra and how I would revamp the teaching of undergraduate algebra with the insights of category theory. And that's tricky because, again, one of the problems with undergraduate courses is that they're so separated out from each other, because really what you want is something that shows category theory shows the relationships between different things, and it's difficult to say what course that should be in other than in a category theory course. But I think that there are certainly ways that those insights could be shown, that some of the definitions like direct products and tensor products and things, and the way that vector spaces are treated and the relationship between vector spaces and matrices are really, well, I found them very baffling when I was an undergraduate, and I found them much less baffling once I understood some category theory. And someone asked about what is called abstract algebra, which is a good question, because I never know actually what people mean by abstract algebra. People mean all sorts of things. Some people just mean category theory when they say abstract algebra. Some people mean group theory. Some people mean something else. And so it depends what you mean. Category theory is a very specific field of mathematics. It involves a very specific definition of a form of algebra, whereas group theory starts with a different, very specific form of algebra and studies those objects. And the thing is that the definition of a category is more general and maybe also more abstract. Maybe just more general than the definition of a group. And so it encompasses more things. And so I don't mean to make it sound like a competition. I'm just saying that category theory can get more meta. And this is a theme that's coming up in a moment with another question. Category theory has fewer, the definition of a category has fewer constraints on it than the definition of a group. And so there are a lot of things that count as categories that don't count as groups, which is why you can study whole fields of mathematics like that. And so you can do things like look at the relationships between topological spaces and groups using category theory. You can't really do it using group theory because those big worlds aren't themselves groups. So that is what I might say about that, that it's really just it's a different field of mathematics that it has a broader aim of what it encompasses. So, right, someone asked about metamathematics, and I don't really know what metamathematics is technically. Often people say, oh, is it something related to this? And then I go and look up a definition and there isn't really a definition. And so I think that probably if there were a definition of metamathematics, it might turn out that category theory is a version of metamathematics, that metamathematics seems to be attempts to study how mathematics works, but there are different aspects of how mathematics works. And so logic, because this question asked about set theory and logic is about how mathematical arguments work. Category theory is about how mathematical structures work. And set theory was also trying to be a foundation of mathematics. And the difference between category theory and set theory is that set theory starts with the concept of a set, which is defined by things being members of a set. Category theory starts with the concept of relationships. And so categories are all built up from the concept of relationships or morphisms, whereas set theory is all built up from the concept of elements being members of membership. And you can move between them because from the concept of membership, you can derive the concept of relationship, and from the concept of relationship, you can derive the concept of membership. It's just a question of what you decide to count as the basic starting point. And in terms of set theory specifically, if you know anything about it, if you know about sets and functions, then category theory takes the point of view that actually the fundamental concept for a set shouldn't be membership, but it should be function. And if you start with the concept of function as fundamental, you can get the concept of set of a membership in a set out of it, and vice versa. And so it's a different point of view. And mathematicians who like category theory, including me, find that category theory more closely resembles how mathematicians actually do mathematics, because the point of it is that things are more based on functions and structure preserving functions between things than on membership of sets. And then some really technical questions about the relationship between with homotopy type theory and quantum mechanics. I don't really understand homotopy type theory or quantum mechanics. I think that homotopy type theory is another kind of foundation of mathematics. It's very, very closely related to category theory, but it isn't actually category theory. And that there's someone asked about two kinds of quantum mechanics being shown to be the same, and whether that was a form of an example of category theory. And I looked it up. I don't think it is. I should check the dates. Hold on a second. Well, I just went down an amazing rabbit hole looking up things to do with the two formulations of quantum mechanics and how they're proved to be equivalent. And I decided that since I was just Googling things, then you could just Google things as well at that point. There definitely is some relationship between category theory and quantum mechanics, because I've been in talks where they talk about bra and ket, and they don't tell me what happened to the C in the middle of the word bracket. Someone asked, is anyone using category theory to study storytelling and story structure? So I Googled that, and the answer seems to be yes. And so that's fun. People are using category theory to study language as well. So it didn't surprise me that there was also that on storytelling and story structure. And someone else asked about applying category theory to a couple of things and what are some tips for starting. And I think that looking out for things that count as relationships is a good start, but also remembering that category theory isn't just about relationships, it's about composing relationships. So when you can build up relationships based on smaller ones. And so that's a really important thing to look out for, I think, when you're starting to think about things categorically. So a final couple of quick questions. Someone very kindly asked if they may translate my work into other languages and share it online because they're worried about copyright, but they long for more people to read the book. Well, thank you very much for that. I'm afraid there is copyright on it, and CUP is busily working on translation rights for various places, and we have sold Japanese and Polish translation rights at this time. And finally, someone said that they came across a quote from John von Neumann: in mathematics, you don't understand things, you just get used to them. And that's very interesting. I kind of like that, because I think that seeking to understand things can be a bit futile, because we never really understand anything. And if anyone thinks they really fully understand something, I think they're just missing something or seeking a much less deep level of understanding. And I think there are a lot of things in life, now that I think about it, that I will never understand. It's like grief, that you never understand why something bad happened. You just sort of get used to it, and you probably don't get used to it either. You just find a way to keep going anyway. And so with mathematics, I think that trying to understand things, sometimes people say to me, oh, I really like your book, I didn't understand all of it. And I think, well, I didn't understand all of it either. And I think that that's where children are really open to not understanding things, because they're so used to not understanding things in the entire world. And whereas adults, we get into this state where we think we're supposed to understand things, and that if we don't understand things, something is wrong. And I remember when thinking about teaching mathematics and who gets stuck, often the people who get stuck are the ones who are so hung up on the fact that they don't understand something that they can't get any further. And often you don't understand one thing until you've got further down the line. And so it's sort of doomed to have to just carry something with you and hope that you understand it later. And I sort of think of it like how I read books in French. I try and read books in French to keep my French up. And I don't look up every word, and I quite often don't understand words. And I just sort of keep going, hoping that I will gradually work out what things mean. And I think that that's my approach to reading and to look at doing math as well, that you might feel like you don't understand something, and then you just sort of keep going to see if you can, how far you can get without understanding it. And then maybe you'll understand it in retrospect later. And so as we go through the book, I hope that you will feel that it's okay if you don't understand things fully, because nobody understands things fully. And maybe actually what separates out mathematicians who are comfortable with math from people who are not is that they're just comfortable with not understanding things. And it's not that they understand things more, it's just that they're okay with not understanding things. And that one of the things that may hold you back the most in getting anywhere in math is worrying about not understanding things. So I think that getting used to things rather than understanding them is a really interesting concept. So thank you for sending me that quote. And this person went on to say that there was an emphasis on manipulation rather than understanding. And it's true that this whole thing can be taken too far. And if you then don't try to understand anything and just manipulate things, then it can get very frustrating. So all of these things are a very tricky balance. And I'm keen to keep going with this and see how everyone gets on. And to know that, yes, sometimes it's in manipulating things that you get used to them. Sometimes you have to do things a bit, just keep going to understand it. It's like the fact that you can't really get comfortable with, you can't really understand how to bake cakes except by baking some cakes and getting comfortable with it. And then maybe it doesn't matter whether you understand what's going on. I don't really understand what's going on with the chemistry of baking cakes, but I've sort of got comfortable with it. Maybe that's a half decent analogy. But at the same time, I have said in this book that I'm not demanding everyone does exercises. And so you don't have to do exercises to keep going with this book. I hope that you will ask me about things that you feel you don't understand. It's not that I'm going to say, oh, well, not understanding it is the point. What I think I'm saying is that we should definitely try to understand things more. Okay, here's what I'm saying. It's great to try and understand things more. I think trying to understand things more is wonderful. And also accepting that we're never going to understand things completely is also really important. That doesn't mean we should give up on trying to understand anything at all. I think that's what the point is. It's like the fact that we can't fix every problem in the world, but that doesn't mean we should stop trying to fix problems in the world, right? We should still try to fix whatever we can. Just realized there was one more question that somehow fell off my sheet about the relationship between some other aspect of category theory and logic to do with something called the Gödel incompleteness theorem. So if you haven't heard of that, then don't worry about it unless you really want to worry about it. But it's something that perplexes a lot of people because it makes it sound like there's something wrong with mathematics. And I don't think it does mean that there's anything wrong with mathematics. It just means that people's expectations of mathematics are too large. because all it says is that at a certain level of expressivity in a logical system, there are things that you can express that you can't determine whether they're true or false, basically because they're self-referentially so looped up on themselves. And so it's not that there are things we can't know, it's that we are able to express statements that can't be either true or false. They can't have a truth value put to them. And the question was whether that puts a limit on how much ambiguity we can eliminate. And I don't think it does. It depends what you mean by ambiguity, but I'm talking about ambiguity in arguments. I'm not talking about ambiguity in truth. There's plenty of ambiguity in truth, and that's why truth is contextual. It's not absolute truth, as we'll come back to. Its truth is all relative to context. But I think that the statement that if we find a statement that according to, because of Gödel's incompleteness theorem, we can find statements that who can't be assigned a truth value. And I don't think that's ambiguous at all. I think it's a very, very clear logical position that there are some things that we can't say, whether they're true or false. And that's, it may be an ambiguity of truth, but it's not an ambiguity of logic. And I think that's what I mean by eliminating ambiguity. And I think I might very carefully say that I don't mean that we aim to eliminate all ambiguity. We just aim to eliminate ambiguity where we can. Like the fact that I aim to eliminate sugar from my diet where I can, but I still eat sugar sometimes. But I wouldn't count that particular thing as a form of ambiguity. And what we try to do is we use our specification of context to try and be unambiguous about what we are saying, even if the truth of that thing in the end. So just like I said in my other book, The Art of Logic, we try to eliminate ambiguity in our arguments. It doesn't mean we're always going to be able to agree. We're not going to be able to agree about things because we're still going to have different political positions, starting from different basic fundamental beliefs. But we should at least be able to reach some agreement about what our arguments are, even if we have to go to quite a high level of abstraction to find it. So finally, thank you for some positive comments. Some people said that they love the book. Thanks for doing this. Thank you for the opportunity to ask questions. So far, I really love your book. Thank you very much. Thank you for the book club. Thank you to the Topos Institute for hosting, and to me for writing The Joy of Abstraction and maintaining the errata list and running the book club. So yes, thank you all for sending in your questions, and thank you to everyone at the Topos Institute for the support for running this, especially Brendan, Juliet, and Tim. And do send your questions in next week for the next chapter. Bye.